Sometimes you need to rephrase or redefine the problem in order to begin to solve it. In this video, you will learn a super powerful technique to solve the classic puzzle of finding the longest increasing subsequence. Say you want to pick the largest possible bouquet of flowers. The rule is that you must pick them from left to right and always pick bigger and bigger flowers than before. You're trying to find the longest increasing subsequence. For example, here it looks like 4 is the longest increasing subsequence you can get. For example, you can pick flower size 3, then 4, 5, and 6. Or another example, you can pick flowers with heights 1, then pick flower 4, then pick flower 5, then flower 9. In dynamic programming, the key is to break the original problem into subproblems that, if you solve them, will guarantee that you solve the original problem. The question here is, what are the subproblems? Furthermore, we're trying to build a recursion. It's very much like mathematical induction, where to prove something for n elements, you prove the base case, then you assume it works for n minus 1 elements, and that gets you the result for n elements. Now, as usual, let's look at the last element. In this case, flower 6. Let's say we knew the longest increasing subsequence that ended in 2. Could we build a longer subsequence by adding the flower with size 6? Actually, we could, so that's not a good example. Let's look at flower 2. If, say, we knew the longest increasing subsequence over all the flowers before 2, would that help us? No, it would not. We found a counterexample. Solving the problem for n minus 1 elements does not give us any useful information for solving the problem with n elements. The reason for this is that we're trying to reduce the size of our problems one by one, when actually we need to make a stricter rule for reducing their size. Let's look at another example, or actually a counterexample. Imagine you have 5, then 10 at the end of some sequence. I'm not showing you the beginning on purpose. Let's say I told you that the longest increasing subsequence, ending in 5, had length 4, because, for example, the hidden numbers were 2, 3, and 4, which together with 5 makes a subsequence 4 numbers long. Now, it just so happens that we can add the 10 to this subsequence, and it gets 1 number longer. So you might think that we could solve the whole problem on all n elements by first solving the problem on n minus 1 elements. But you would be wrong. Let me show you a counterexample. Let's say the hidden numbers were 2, 3, 4, 6, 7, and 8. Now the longest increasing subsequence ending in 5 is still 4 numbers long, but the longest increasing subsequence ending in 10 is 7 numbers long. What we are seeing here is that to get the longest increasing subsequence overall, it's not enough to reduce your problem by 1 element. We need to reduce the problem in a much stricter way. The key here is to strengthen the induction hypothesis. Instead of assuming we solved the original problem for n minus 1 elements, let's make the rule a bit stricter. Instead of looking at all the elements before the last one, we'll hypothesize only on elements that are potential candidates for the increasing subsequence. To be a candidate for the increasing subsequence, you need 2 qualities. You need to be less than the last element in value, and you need to appear in the list before. With those restrictions, we'll form the subproblem out of the elements listed before the last element and with a value less than the last element. For example, if our last element is 6, then let's get the longest increasing subsequence for the sequence ending in 2, ending in 5, ending in 1, ending in 4, ending in 1, and ending in 3. That is, from the point of view of this last element 6, we are totally not interested in the longest increasing subsequence ending in 9, because 9 is greater than 6. Now, once we get all these longest subsequences, we'll take the maximum over all of them. But wait, we're not done. We need to do this for each element in our list. Let's continue the example. We now take the second to last element, the flower size 2. Here we'll take the maximum longest increasing subsequence that ends in 1, and then we'll take the maximum increasing subsequence that ends in this other 1, and those are the only smaller elements than 2. So continue this way until we get to the beginning, and then we take the maximum of all these n values. In essence, what we did here is redefine the problem. The original problem asked to find the longest increasing subsequence over n elements. The redefined problem says, nah, that's too weak. If you want to find an increasing subsequence, you need to use your muscles. Limit yourself to maximizing only over the elements that are strictly less than the last element in your list. By redefining our subproblems to be stricter than the original question, we were able to compose an algorithm to solve the whole problem. You might be asking yourself when to use this technique. One hint could be that you start with the weaker induction of just reducing the size of the list by 1. But if you can come up with a counterexample, like you have here, that knowing longest increasing subsequence ending in 5 is 4 numbers long doesn't help you to get the answer for the longest increasing subsequence altogether, then you know you need a stronger induction hypothesis. Or in other words, redefine the subproblem to be more constrained than the original problem.